All right. Okay. Relax. We're going to change topic today and discuss about system of ODEs. In principle, whatever it is in these lectures, we already have covered it. I just want to redo it in a more organized fashion, so that way it can lead us to nonlinear system of ODEs and learn some interesting things there. So let me just say the following for those who are not here, and I'm sure they will be listening to the video. There is going to be an exam problem from the lectures from now to next Wednesday. It's going to be at least 20 to 25% of the grade, even though there's not going to be a homework. So you have to pay attention, and in some sense consider this as a free bonus, because if I say something, it will be fresh in your head, and it will be very useful material for the exam, okay? And there will be nothing more than what's in the notes, but there's gonna be something in the exam, can be 20, 25, 30 points from the lectures today, next Monday, and Wednesday. All right, so we're gonna talk about system of ordinary differential equations. If you remember, you know, this is like the systems of the form dx over dt equal ax, and those systems lead to the exponential of a matrix, right, e to the at. So what I want to do is I want to revisit these problems in a little bit more details and discuss some qualitative aspects of the solutions to these problems. And qualitative means basically plotting some sort of an approximation of how the solutions may look like without actually solving them, if possible. Okay, don't pay attention to your computer, because I'm going to be doing a lot of jumping, starting from now. All right, so the system of equations we're going to look like would be like the equations that you see on the bottom. So this is a system of, in general, the way it is written, of nonlinear ODEs. T is the time. Obviously, I have to provide you some initial conditions for time t0, x1, 0 to xn 0. And actually, in a rather straightforward manner, you can show that if these functions are continuous and the derivatives of these functions are continuous, then there is a solution to some interval around the initial condition. Okay? We're not going to be discussing today the nonlinear system of ODEs, so we will simplify this with a linear system of equations, but most science and engineering problems take this form, okay? Prime here, by the way, means time derivative, okay? So just to simplify the notation. Even if you have a system that is a second order, let's say, differential equation, or a third order differential equation, you can actually write it as a system of first order ODEs by defining new variables. So for example, if you have a system that involves second derivatives, you can define some new variables, x1 to be the displacement and x2 to be the velocity. So you can transform a second order system to two equations of first order, right? So these equations are in some sense universal. They come all the time. Every fluid mechanics problem looks like this. Any dynamical problem looks like this. You just mention it, everything is like that. All right, let's see what jumping we're gonna do now. So if it happens that those functions are really linear functions, the way that you see on the bottom of the slide, so these are first order linear systems, and they are linear because there is no x squared or x1, x2, or anything like that. They are linear in the x's. But the coefficients are allowed here to be functions of time. And also, you know, I noticed some forcing terms, okay, that they're all functions of time. So you can solve extremely easily, actually, that if you put some initial conditions at some time t0, and these functions p and g are continuous in some interval, then this system of linear ODEs has a unique solution in that interval. So here, actually, because this is a linear problem, the derivatives with respect to x1, x2 are these coefficients. So really, you don't need to put an extra requirement of continuity of the derivatives if you say that these p's have to be continuous, all right? So bottom line, these problems do have a unique solution. Okay, so what I'm going to do is first, I am going to do some extremely minor revision of linear algebra to introduce a little bit of complex numbers. Nothing new, okay? So the first thing so if we work with vectors that can have complex components, all right, we need sort of to modify what an inner product between two vectors x and y means, right? Up to now, if I give you two vectors x and y, the inner product is really the summation of xi. You remember that? Now, I'm going to sort of enhance that definition, and I'm going to take the definition of the inner product between two vectors x and y to be the summation of xi complex conjugate of yi. Okay? With that definition, when you look at the magnitude of a vector x, there is a conjugate there, xk bar. All right? So if you see anything that has complex numbers in it, please just use this definition of the inner product. And I'm saying this because when you work on this linear system of equations, it's very possible your eigenfunctions may come to be complex. So you need to be sure that you know how to simply do an extension to complex numbers. So for example, with this definition, if I give you a vector that is a plus bi, this definition makes a sense because according to this definition, the magnitude of x is a squared plus b squared. And you know how I get this, right? abi times a minus bi, all right? So, or following this definition, a squared, all right, plus b squared. Okay, so that's the definition of the inner product so if, for example, if I want to take find the magnitude of this vector, you notice here I have 3 minus 4i, right? So 3 4i plus times 3 minus 4i. Nothing new. Okay. Obviously, we're going to write equations in terms of matrices, right? So, you know, you have to use common sense when it comes to some notation. So if I have a matrix, for example, 2 by 2 that you see here, and I write a of t, means that every component of this matrix is a function of time. All right, so you can see here, everything is a function of time. Now, when you do operations on matrices that they are functions of time, and operations means, you know, addition, multiplication, or even more exotic things like taking derivatives or integrals, for the context of this course, when you see anything that operates on a matrix, means you operate element-wise. Whatever you do on an element, you will do now on the matrix. So for example, if you want to find derivative with respect to time, this will be 6 times t cosine of t minus sine of t and 0. And the same thing about the integral. So nothing new. If you want to say take derivatives of a matrix, you take derivatives of every element. Now, there are other sort of definitions that they are very relevant in other type of calculations, but for our course, everything is element-wise type of operation. Okay. So you remember when we had we were talking about matrices. We were talking about a system of you know, linear independent vectors. So we need to do some extension here because if you think trying to solve dx over dt equal ax, right, and you find some particular solutions to that system of equations, obviously those solutions are functions of time. So really what we're playing with, they're not simply vectors, but they're vector functions, right? So when we say here is some characteristic solutions of dx over dt equal ax, those solutions are functions of time. So nothing new. For example, the k characteristic vector, we have components x1, x2, xm, but you notice I keep the k to remind myself that k goes from 1 to n if the matrix A is n by n. And obviously, we will do examples on this. So we work with vector functions rather than vectors. And right now, we assume these vector functions to be functions of time, obviously. And the only thing we have to do is we need to extend the concept of linear independent. So if somebody gives you before, let's say, 10 vectors, you know what the definition of linear independence is, right? If you take a combination of these vectors equal to 0, the only way to get that is if all the coefficients are equal to 0. Now there is time there. So what we need to do is we need to actually add the requirement for all times in the interval of interest. Okay? I am going to give you ahead of any derivations or anything like that, for what we're going to do in these lectures, if you actually show that, let's say, these vectors x1 to xn are linear independent at some time t, then they're linear independent at all times. And actually, this makes a wonderful little exam problem or homework problem, okay? So if they're independent at one time, they're independent at all times. So you don't really have to show, you know, do anything fancy about these time dependence. Okay, so that's 21. And let's move to 22. And I'm going to do some reminders from linear algebra again. So if you remember, we're solving, obviously, eigenvalue problems. So we have a matrix A, we find the eigenvalues. I want you to remind you two different terminologies, the algebraic multiplicity of an eigenvalue and the geometric multiplicity of an eigenvalue. So I remove them, so you guys tell me, what's an algebraic multiplicity of an eigenvalue? I mean, again, you know, if there are two possibilities here, if you tell me one, even if it matches the other concept, we're okay. So what's an algebraic multiplicity of an eigenvalue? Common sense definition. Well, so I have a matrix n by n, right? I compute different eigenvalues. So let's say I compute one eigenvalue lambda. What is the algebraic multiplicity of lambda? How many times that lambda is an eigenvalue? Because, for example, when you have the characteristic polynomial, you may get, let's say that eigenvalue is lambda 1, so you may get lambda minus lambda 1 to a power 5. So lambda 1 has an algebraic multiplicity of 5. And what's the geometric multiplicity of an eigenvalue? How many eigenvectors independent eigenvectors I can have to an eigenvalue that has algebraic multiplicity 5? How many independent eigenvectors I can get for an eigenvalue that has algebraic multiplicity 5? 5 or less. All right? So that is the geometric multiplicity of the eigenvalue. Okay? And obviously, when we solve dx over dt ax equal to ax, the eigenvalues and eigenvectors are going to come to play a role, which means somehow we're going to have to do strange, weird things, but nothing complicated, depending on what the algebraic and what the geometric multiplicity of the eigenvalues are. So remember what's algebraic, remember what is geometric, and what I will remember is that I have to move to the next slide. Actually, I don't have to move to the next slide. I have to move a little bit further down. Because we operate with, in general, with complex numbers, all right, for the lectures today and the next few lectures, you remember when the most wonderful situation with the eigenvalue problem was when the matrix was symmetric. And I will summarize for you all the outcomes of what it means to be symmetric, okay, in the context of eigenvectors and eigenvalues. But obviously, we have to generalize what symmetric means when we have complex matrices. And the generalization is very simple. Instead of symmetric, we call the matrix to be Hermitian. All right? We denote it. The Hermitian of a matrix is A star, and the matrix is Hermitian when A is equal to A star. So this is similar to A equal A transpose. So what is A star? Is A transpose conjugate. So not only you take the transpose, you take the conjugate as well. All right? again, for those, for example, who are going to take courses in linear systems and dynamical systems later on, you will see all the matrices you will work with will be Hermitians, okay? So again, Hermitian is nothing else. So if you look at the ij element, aij is not equal to the aji, but to the conjugate of aji. All right, so remember, symmetric now becomes Hermitian. No big deal. And we can move to the next slide. And I'm going to remind you all the good things if the matrix is symmetric. And by generalization, we're not proving it here, but if the matrix is Hermitian, here is what I want you to remember, or you should already know this. All the eigenvalues come to be real, okay? You have a full set of n independent eigenvectors. It doesn't matter if one eigenvalue has algebraic multiplicity of 5 or 6. You can always find n independent eigenvectors. If you take two eigenvectors that correspond to two different eigenvalues, you can prove that they are orthogonal. And as I mentioned before, if you have an eigenvalue with multiplicity, algebraic multiplicity m, you can always find m orthogonal eigenvectors corresponding to that eigenvalue for Hermitian or symmetric matrices. Right? It's very important. So symmetric is wonderful because for an n by n matrix, you can guarantee that you will find n independent orthogonal in principle, right? You can orthogonalize them, eigenvectors for this matrix. All right, nothing new there. So let's move to the, solving this system of equations. So I'm going to write the system of equations to this nice matrix form. So it's a linear system of equations defined by this matrix P. So all of these elements of P are functions of time, and there is a non-homogeneous term G of T. I will do actually this particular problem if we reach that point today at the end of my lecture, but certainly we can do further simplifications here. For example, you may work only on the homogeneous problem, and instead of having everything a function of T, you can make all the elements here to be constant, right? So you can solve x prime equal ax. But this will be a nice problem if we can reach that point and we can actually discuss this particular problem. Okay. With your permission, all right, with your permission, I can, for this particular problem, I can jump directly to the solution of it. And the solution of it says that if you can find me n independent solutions of this particular homogeneous problem, so if you look at x prime equal p of x, and you can find me x1, x2, xn, so the general solution is what you see up here. Right? I'm not telling you anything new, right? So, it says if you find n independent solutions, this is also a solution, and actually it is the general solution to the problem. You can actually immediately prove that this is the solution because if you plug in this inside this equation, because x1, x2, xn satisfy the equation, you will immediately see that the answer is correct. Okay? So the question is now, how do you get actually for this linear problem, how do you get n solutions x1, x2, xn? Can somebody guess on what will be sort of, so it's a dynamical system, right? How can we get n independent solutions? What will be a nice way to get those? So x is an n-dimensional vector. So what will be a nice way to actually get x1? How about if I start with initial condition 1, 0, 0, 0, 0, 0? Will that give me one vector? Yes? How about if I start with a vector 0, 1, 0, 0, 0? Will that give me an independent x2? All right, so this is what we need to do. If I can find. All right, so if I can find this, so we're going to start with initial conditions that look like this. So I'm going to get one solution that is my characteristic solution x1. This will give me x2. This will give me xn. and then the linear combination of those vectors will actually be the solution to the general solution to my problem. There were some important slides that I omitted. I want you to look. There is nothing sophisticated in any of the slides, so actually you can read them while you're drinking coffee or you're eating turkey. So they are very simple, but really this is a nice way to generate n-independent solutions to this particular problem. All right, let me see if we're done with the review. So we're going to limit ourselves, to start with, to this linear system where all the coefficients are constant. So we're going to play with a system x prime equal ax, where all the coefficients in this matrix A are constant. So this will be sort of the most trivial case, so we don't have to worry about time dependence. So you already know the solution to this problem, right? This was in your exam also. You remember x equal e to the 8x, but I want to revisit and see a little bit more fancy things that we haven't really had time to discuss in any detail in previous lectures. So let me remind you a few things first. So I'm going to take a one-dimensional problem. So let's say my differential equation is x prime equal ax. So instead of having my matrix equation, I have a scalar equation. We agree that the solution is some constant e to the at. Correct? Now, can somebody remind me what is the equilibrium point of an ordinary differential equation? If there is one, so what's the equilibrium point in general? How do you identify it? Remember, this is a dynamical system, right? So equilibrium means, when you reach there, you don't want to leave from there. So in essence, the time derivative is equal to 0. So the equilibrium point for this equation is which point? X equal to 0, all right? So my equilibrium point is x equal to 0, and I'm assuming, obviously, that A is not 0. Otherwise, this becomes a trivial problem. And so if you look at this equation here, right, you would like to know if you start from somewhere for some initial condition, will you actually approach with time the equilibrium point? So look at this equation and tell me, as t increases and goes to infinity, is this solution going to 0, to the equilibrium point? Or under which conditions will it go? For A what? For A negative. Can you see that? If A is negative, as t goes to infinity, the solution will go basically to the equilibrium point, which means if A is negative, all right, my solutions basically are I'm having an asymptotically stable solution. Asymptotically means as t goes to infinity, my solution approaches x equal to 0. Now, if A is positive, obviously what happens to the solution? Goes to infinity. It's unstable. So what I would like to do is, in the lecture today and maybe the Monday the following week, I would like to actually extend this idea for this simple equation to our system x prime equal ax, right? And obviously the equilibrium point will be, again, x equals 0, but that's a vector. And I want to figure out if x equal to 0 is asymptotically stable, if all solutions will actually, as t goes to infinity, will reach x equal to 0, or if it's an unstable point. Unstable in the sense that if I start a little bit away from x equal to 0, all the solutions will go to infinity. Okay? So we would like qualitatively to discuss about this type of things. All right. So one of the ways that we're going to do qualitative discussion of the solutions to this system of ODEs is to actually analyze the solutions on for example, I'm looking here for an ODE, a system of ODEs that has only 2 variables. Actually, if I can go back rapidly, come on. This is the system of equations I look, right, only for 2 variables. So if we try to, don't want this. So if we try to sort of discuss qualitatively what type of solutions we get, an easy way to do this is to plot trajectories on the plane of x1 and x2. And what trajectories means, if I start from some point, how will the solution look, x1, x2, look on this plane? All right, and this is what we call the phase plane, okay? And so we will actually plot a lot of these trajectories for different initial conditions. Now, this is not anything different from what you already have done for, you remember for, what was it? What type of differential equations you already did this? You qualitatively, right, plotted things on the phase plane before. No? Did you plot the derivatives at any time? So effectively, you know what you plotted? When here I say here's a trajectory, what actually you plotted was the tangent to that trajectory. You remember? The derivatives, correct? And the derivatives for this problem, you know what they are? These are the derivatives. A1, 1x1, A1, 2x2, and A2, 1x1, A2, 2x2. This is what you plotted before, but we'd like to do this for system of linear ordinary differential equations. Okay, so let me see if this is a slide I need to talk today. Looks, the answer is yes. So let me, without telling you, here is a system of two equations, linear equations. And if I do, if I plot these different trajectories on the phase plane, this is how they look like. So I want you to look at them and tell me qualitatively something about the solution. I mean, summarize with words, what do you see here? So, you know, these are all the trajectories, and all the trajectories seem to go where? To what point? 0. So this looks like a stable point. But it's even more important, actually. They go to 0, but do you see anything very nice happening at the point 0, 0? So you notice there is two lines here plotted. This line x1, and this is another line x2. Can you tell me something particularly looking at around that point? What are the tangents of all of these trajectories at 0, 0? Visually. So this is a line, right? What can you tell me about the slopes of all of these trajectories at the point 0, 0? They are basically the slope coincides with that line, okay? So all the trajectories seem to converge with the same slope as this characteristic solution x1 and that you see here. And then you can see some weird line here, x2. Can you guess what x1 and x2 will come to be for this particular problem? No, but what, you know, I'm plotting x1 and x2. What is x1 and what's x2? My system of equations is 2 by 2. I have two equations, two unknowns. So what do you think x1 and x2 will represent? Which vector? Eigenvector. So it will be basically, you remember we said we have two independent solutions, okay? So x1 and x2 will turn out to be this characteristic solutions, these two independent solutions to my system of equations, okay? And obviously we're going to have to compute those. We're going to have to show how actually we compute this for this particular problem. So in this case, again, all the trajectories seem to approach 0, all right? So this equilibrium point is stable, and the slope seems to be the same as x1, and then there is this characteristic solution x2 that sort of has its completely own slope, irrelevant to anything else, right? So x1 is like that, and x2 is like that, and obviously I can maybe ask you, so what is that? Is that a special trajectory? How is it possible everything to have the same slope as x1 but not x2? Well, you remember when you get solutions to this system of equations, as t goes to infinity, it is possible that the characteristic solution x2 for t going to infinity, it's irrelevant. Because, you know, maybe it goes to infinity way too fast, and you know, maybe x1 dominates basically when it comes to the behavior of the system at t going to infinity. So we will see this. All right? So let me discuss a little bit about the algebra. Again, we have a system of two equations with two unknowns. We are plotting the trajectories, and actually we're plotting the slope of the trajectories. So I'm writing the slope as dx2 over dx1. I can write this like this from the definition of the derivatives. So this is equal to that, and this is equal to that from my system of equations. Everybody agrees? So really, if you want to, if I give you the matrix A, and I ask you to plot something like that, effectively what you will need to do is take the right-hand side here, plug in different values of x1 and x2, and plot it, and it will look like this for some particular matrix A, okay? All right, now, the idea here is at any value of x1 and x2, all right, there is a unique tangent direction that you can compute with this formula, but this formula doesn't work for one particular case. And what is that one particular case where the slope doesn't seem to be determined correctly by this formula? That particular case is when the numerator here is equal to 0 and the denominator is equal to 0. And when is the numerator equal to 0? And when is the denominator equal to 0? You remember my system of equations is x prime equal ax. And you can actually see it here. When is this equal to 0? And when is that equal to 0? What x1, x2 are you getting for that point? How do we call that point? So basically, this will become 0, and this will become 0 when these derivatives are 0. And how did we call that point? That's the critical point, all right? In our case, that's, let's say, the point 0, 0. So effectively, a critical point, you can actually set, you know, by setting ax equal to 0 and assuming a is not singular, and you can say the solution to that is x equal to 0. Another way to look at this is a point where the slope of the trajectory passing through that point, it's undetermined. All right? It's undetermined. And what does this mean, it's undetermined? Actually, looking at this graph, you may say, but all these trajectories have the same slope as x1. Yes, but there is another x2 there, and it doesn't seem any of the trajectories having that slope. All right? So all the trajectories have the slope of x1, but the solution is not just x1. It will involve x2, and no trajectory seems to have the slope of x2. So in this point, effectively, the slope that you see here, it's undefined, and that's another definition of a critical point. All right, how do we get actually the solutions to dx over dt equal ax? Again, this is a review from our linear algebra lectures. Look at the bottom. Do you remember that trying to solve x prime equal to ax, the solution is actually of the form xi e to the rt, where r comes to be an eigenvalue and xi comes to be what? An eigenvector. You remember that? Right? If you plug it in actually directly, right? X prime will be r times xi e to the rt, and ax will be ax e to the rt. So when you cancel e to the rt, you get axi equal r times xi, which is the eigenvalue problem. So the solutions basically that we're looking are of the form eigenvector times e to the rt. So remember this, okay? There may be other solutions, right? There may be other solutions, but the easiest ones are xi e to the rt. And there may be other solutions if, for example, r is an eigenvalue that has some algebraic multiplicity that is higher than 1. Right? So there may be another solution that may look a little bit different, but for the starting point is xi e to the RT. All right. So let me take one example, okay? And the previous slide basically have all the algebra for you to see that there's no magic. So this is my system of equations, 2 by 2. So you're going to have to calculate the eigenvalues and eigenvectors of this. And I already have done this in the previous slide. And then I claim that the two characteristic solutions are this that you see here. So obviously the two eigenvalues are what for this matrix? Lambda equal to, or R equal to what? What are the eigenvalues of this matrix? R equal to 3 and R equal to -1. And the two eigenvectors is, the corresponding eigenvectors are 1, 2, and 1, -2. Okay? So you can actually show that these two solutions are independent by calculating the Wronskian. And the general solution, again, looks some constant times this solution, right, plus C2 times that. This is what we did in earlier homeworks on linear algebra. So this particular problem has two distinct eigenvalues, 3 and -1. So we can compute two eigenvectors. And the general solution looks like that. So I'm going to try to actually plot this solution. All right, so we're going to try qualitatively to plot the solution to see if we can get some explanations on the plots we had on the phase plane earlier. So I'm going to try to visualize the first part of the solution, that is C1 times X1. So I'm going to assume that C2 is equal to 0. So I'm only going to take this solution. Now, if C1 is positive, this solution, what happens to this solution as t goes to infinity? If C1 is positive, where is the solution going? To infinity, okay? And obviously, if C1 is negative, then this goes to minus infinity. But can you tell me, if you take a trajectory based on this solution, what is the relation between x1 and x2 on this trajectory? So, we say the solution as t goes to infinity, but what is the relation between x1 and x2 looking at that particular solution? What's the direction that it goes to infinity? Does it go in any direction or in a particular direction? Around here? Yeah, so 2x1, you can see 2x1 equal to x2. Everybody can see that? 2x1, right, is equal to x2. I mean, you can see x1 is 1 times e to 3t. X2 is 2 times e to 3t, so 2x1 equal to x2. So you remember this beautiful line that I plotted before, right? So the line that I plotted before and I said corresponds to the solution x1 was actually the line x2 equal to x1. We will see this in case the example is a little bit different, but this will be one of the lines that the trajectories will follow as they go to infinity. All right? How about the second solution? Immediately you can see here that 2 times x1 is equal to minus x2. That's another line. So let me plot all of these lines. Here they are. Here's my line x1, and here's my line x2. And what can you see? All right? Can you see now that as t goes to infinity, all the trajectories, regardless of where you start, they're actually going to infinity, but in a direction parallel to what vector? So as t goes to infinity, looking at this plot, just forget the mathematics, right? Looking at this plot, the slope of all the trajectories as t goes to infinity is in what direction? What is the slope? 1, 2. And why is 1, 2 and not 1 minus 2? Because what term from these two terms dominates as t goes to infinity? Is this the big term or this is the big term? The first term. Can you see that? Because the other one is e to the minus t is 0. Makes no difference. So as t goes to infinity, everything it dominates with this particular term, and you can see the different trajectories basically go to infinity as t goes to infinity in the direction of x1. And obviously, you can now make the same arguments about t going to minus infinity. All right? So which term dominates as t goes to minus infinity? This term, correct? Because if t goes to minus infinity, this will drop out. So this is the dominant term. Can you now see the trajectories actually as t goes to minus infinity? They're following, I'm sorry, what is that? They are following this line here, parallel to x2. I have to go away because I cannot even see the errors of this, on this particular solution. So where is t minus infinity? Can you tell me? Tell me what quadrant I have t minus infinity. Because I see here, this trajectory is here. They follow the line x1, so this is as t goes to infinity. So where is t minus infinity? It's here. Can you see that? Can you see that's t minus infinity, and then you are basically following the trajectory x1. Okay. So the origin, in this case, we call it to be a saddle point. And obviously, it's an unstable point because all the trajectories run away from 0, 0. They go to plus infinity or minus infinity. Can you tell me why I call this a saddle point? And the good way to look at the saddle, you remember in optimization problems, maybe in your old courses, when you have a function, you say a point is a saddle point. What does that mean? That function in one direction does what? It increases, and there's another direction that decreases. So can you tell me something analog here that allows us to call this a saddle point? So we had two characteristic solutions, all right? So can you see in the direction of x1, the solution goes to infinity away from the origin, and in the characteristic solution x2, the solution does what? It goes towards the origin. All right, so this is a saddle point. So you need to be able to characterize what type of equilibrium points you have, and you will see obviously in the lectures there will be many other categories that we will have to discuss, but this is a saddle point. Again, easy to remember. The directions, all right, they are opposite in the two characteristic solutions. And you know what? Another way easy to remember, the problem has two eigenvalues. One is positive, one is negative, right? So one positive, one is negative. So one characteristic solution will go to infinity, the other one will go to minus infinity. All right, so this is slide 55. And let me do a jumping. So this is a slightly different system of equations. So my metric A is this, just another example. I compute x1 and x2, and I plot it. And I want you to discuss for me what you actually see and how this example differs from the previous one. Look at this plot and tell me how the solution differs from the previous one. I haven't done anything but compute the eigenvalues of this, compute the two eigenvectors exactly as we have done. And you remember the solutions are the eigenvector times e to the minus lambda t. So obviously the eigenvalues are lambda equal to -1 and lambda equal to -4. So the difference from before here, both eigenvalues are negative. They have the same sign, actually. Okay? So look at these two solutions and tell me how this differs from what we had before. The behavior looks to be very different. So I can see all the trajectories, right, coming towards the 0 point, and they are tangent basically to x1. But what else do you see? You remember before we had some of the trajectories deviating. So here what happens to all the trajectories? So it doesn't matter where you start. Where are you going to be as t goes to infinity? The origin. So what type of point, how should we call this? Is this point a stable point? All right, so that's a stable point, okay? And this point is called a node, okay? It's called a node. And in this case, it's a stable node. And I call it asymptotically stable just to refer to the case as t goes to infinity. So all the trajectories basically will lead you to 0, 0. Again, how easy is to identify both eigenvalues have the same sign, in this case, negative. How about if the signs of the eigenvalues were positive? This will still be a node, but where are the trajectories going to take if the eigenvalues are both positive? Will take you out. So this point will be basically an unstable point, okay? An unstable node. Okay, so we're slide 65. Let me jump to a nice number, 67. Actually, there's nothing new there, so we're not interested. It repeats the same things. So you know what I'm going to do is I'm going to jump to slide 68. Okay? So this is actually what we already discussed, before. It just gives some more intuition on the particular case that we had a node, okay? So again, you notice there is two characteristic solutions x1. There is 2x2. Both of them lead you to 0, 0. And all the paths, all the trajectories have the slope of x1, okay? And the eigenvalues for this particular problem is e to the minus 4t and e to the minus 2t, okay? How about this case? I mean, is it possible that somehow for some metric A you may get this? So effectively here, if you give me any direction, there is a trajectory that has the same slope. All right, so if you give me any direction, I can find you a trajectory with some initial conditions that has that slope, okay? This is what we call a proper node, and here is one example, all right? If you take your matrix A to be this diagonal identity matrix, you can actually show that this is the situation that you are getting in this particular problem. Okay. Let's make life a little bit more complicated. And again, we have seen this already. Let's say that somehow when you calculate the eigenvalues, you get actually some complex eigenvalue, lambda plus I mu. And you remember, because we're working with Hermitian / symmetric matrices, if lambda plus I mu is an eigenvalue, lambda minus I mu is also going to be an eigenvalue. And the same can be said about the eigenvectors, okay? So the eigenvectors basically corresponding to lambda plus minus I mu will be a vector that has the form A plus IB and A minus IB, okay? So the question is, will you be able to write down? We already have done this. If I want to write down two independent eigenvectors corresponding to this complex eigenvalues, can you tell me in terms of A and B and in terms of lambda and mu, how these eigenvectors will look like? Remember the general solution, regardless if this is complex, the general solution, you know how it looks like? Xi, the eigenvector Xi, e to the RT. And e to the RT will have a real component, which is e to the lambda t. And then we'll have cosine of mu t and sine of mu t. So how do the two solutions will look like? Will they look actually like what you see on the bottom? Does that sound familiar? The proof of this is actually, just as a reminder, it's on the next slide. But if you take, an eigenvector in the form, let's say, A plus IB times e to the lambda plus I mu, and you write down the real and the imaginary parts, and you extract the real parts and the imaginary parts, this is what you get. And you remember the behavior as t goes to infinity is defined by the real part of the eigenvalues, and then the imaginary part defines how the solution oscillates as it goes to 0 or to infinity, depending if lambda is negative or if lambda is positive. So let me show you how the solutions and the trajectories will look like for this particular case. So here's a matrix. All right, so if you actually go and compute the eigenvalues, can you actually guess? Can you tell me what are the eigenvalues of that matrix looking at the solutions? Guess what are the eigenvalues for this matrix? Plus, minus, I. Okay? So this is one solution. This is another solution, right? So this is the characteristic solutions. And you notice in this case, because this is e to the minus t and e to the minus t, so they approach, obviously, as t goes to infinity, they approach the equilibrium point 0, 0. But they approach it in an oscillatory manner, all right? So we call this a spiral point, all right? Because it spirals towards 0. And in this case, it's a stable point because the real part of the eigenvalues here is negative, is -1/2. And obviously, you can have an unstable spiral point if the real part comes to be positive. But so instead of converging to 0 asymptotically, it will go in a spiral to infinity away from 0. Let me see if there is, I already lost 2 in the audience, but they are semi-sleeping in most of my lectures, so it's okay. It doesn't bother me. So here's a particular problem, all right? So this is, I think it's actually the same problem with a different matrix, okay? So you can see the spiral going to 0, 0, so that's an asymptotically stable solution. I thought maybe I have something that diverges. I don't have it. But can you tell me actually on this problem, let me just put a plot. When do we get this situation? Remember before we had real and imaginary parts. The real part gave us how it decays with time, the imaginary how it oscillates. Here we seem to get circles. When do we get circles? The real part is not there. All right, so we have a pure oscillation. Now, this is obviously a stable solution, right? It doesn't escape to infinity, but it's not asymptotically stable in the sense that as t goes to infinity, this solution doesn't go to 0. It's on circles. So it is stable, but it's not asymptotically stable, right? It doesn't drop down to 0. It's 11:23, and I think this will be a good point to stop. What I would suggest is that you read the rest of the slides. I'm going to do them the Monday after Thanksgiving. They have lots of examples, mainly what happens when an eigenvalue has an algebraic multiplicity. So that is examined. And then how do we solve the non-homogeneous system of linear ODEs, and a little bit discussion on stability at the end of the slides. So we will do this after Thanksgiving. There will be office hours tomorrow if anybody's still around. If not, have a good Thanksgiving. Drive safely. I heard there is snow. My phone was beeping this morning about snow warnings here and there. And you don't drive. You don't have a license. That's good. All right, so I'll see you. Well, see, you look at me like, you know, it's fine. All right, see you next week. Next week? Yes, of course. Yes, of course, yeah.